Hello guys, welcome on Tesla Adventures. Today in this video we are going to discuss the very important topic of gravitation, which is Hohmann orbit maneuver system. You all know about the successful mission of India on the Mars Mangalyaan, and in that mission this orbit maneuver system was used to for the satellite to make it revolve around the Mars in its orbit. So let us discuss that what is this orbit maneuver system and what are its calculations. So first of all, let us see that there is a planet and there is a circular orbit in which a satellite is revolving in this circular orbit. So we know that the orbital velocity in this circular orbit. So let us first of all define that v1 is the orbital velocity in the smaller circular orbit, and v2 is the orbital velocity in the larger circular orbit. Okay, so v1 will be equal to under root of gm by r1, and v2 will be equal to under root of gm by r2. These are v1 and v2, which are orbital velocities of these orbits. But we need to transfer the satellite, which is initially revolving in this orbit, circular orbit, to the bigger circular orbit through this elliptical path. So what we need to do is the fact that first of all we need to give a impulse, and that impulse is given to the satellite by impulsive rocket firing. So the rocket firing, you all know that satellites is being equipped with the small rockets in different directions, so that we can change the direction of satellite by firing the rocket in opposite direction. So when the satellite is revolving in this circular orbit and it is at this point, we fire a rocket in the opposite direction so that the velocity of this satellite increases. So first of all we need to find out this delta v1, which we need to give that satellite so that it comes into this elliptical orbit. Now we know that in elliptical orbit, first of all let us discuss this elliptical orbit. So in this elliptical orbit you can see that center of earth is this one, and this distance, this complete distance, you can see this is the semi-major axis, and this semi-major axis is equal to r1 plus r2, you can see. So semi-major axis is r1 plus r2 by 2, and this is the major axis. So semi-major axis is r1 plus r2 by 2. Now we know that when the satellite is at this point, its velocity, this velocity is equal to, we can find out its velocity by the formula. This is the maximum velocity because this is the planet and this point is perigee, so this is v max. So it is under root of gm by a, which is the semi-major axis, into 1 plus e upon 1 minus e. But due to the fact that we don't know the value of e, okay, so let us use the energy conservation at this point. So we know that at this point the initially this satellite was in circular orbit like that. Let us draw this circular orbit. So initially this satellite was in a circular orbit, and this is the planet. So the initial energy of satellite, total energy before firing, before first firing. So total energy was minus of G m m by r is potential, and r is this one, so this is r1, so this is r1, and the kinetic is plus of G m m by 2r1 before firing. And after firing that rocket in the opposite direction, in this direction, we have increased the speed. So the total energy after firing first rocket, okay, or first thrust or first jet, we can say anything. So the total energy would be the sum of potential plus kinetic, but potential would still remain the same, because potential depends only on the distance of that satellite from the center of the planet, which is again the same in this case. So potential would be minus G m m by r1 plus the new kinetic energy would be half m v square, or let's suppose v1. In fact, let's suppose v0. This is the new kinetic energy. So we know that the total energy will change obviously, and the new total energy will be equal to minus of G m m by 2a, where a is the semi-major axis, which is r1 plus r2 by 2. So you can see that half m v0 square is equal to minus of G m m by r1 plus r2, and this is plus G m m by r1. So you can see that cancelling m with m, v0 square by 2 is equal to, what I've done, I've placed this value of a in this equation. So 2 is cancelled out, and I'm taking common GMM. So GMM is common and m is cancelled obviously. So taking out GMM common and cancelling this m, we can see that it would be 1 upon r1. This is 1 upon r1, and you know that this is 1 upon r1 and this is 1 upon r1 plus r2. Okay, so v naught square by 2 is equal to G m upon this is r1 into r1 plus r2, and when I will take the LCM, then you can see it would be r2. So v naught is equal to 2 r2 by r1, and this is r1 plus r2, and the root of this. This is the new velocity or the new speed with which this planet would start to move in the elliptical orbit, and therefore the delta v1, which is the first impulse which we need to give to the satellite, would be equal to the new elliptical path velocity minus old orbital velocity. So old orbital velocity, we have already discussed that old orbital velocity was gm by r1 under root gm by r1. So delta v1, which we need to give to the satellite, is under root of, this is delta v1 is equal to under root of 2 r2 by r1, and this is r1 plus r2, minus under root of gm by r1. So we can take common, and we can write it down as under root of gm by r1, and inside the bracket it would be 2r2 by r1 plus r2 minus 1. Okay, you can see that. So this is the first impulse which we need to give to the satellite so that it goes into the elliptical orbit. Now at the point of apogee, this is the point of apogee. So if this satellite is moving in this elliptical orbit with the speed of v0, which we have already calculated at this point. So at this point the speed would be v0 dash, because we know that the speed changes. So this is the center of the planet, and this distance is r1 and this distance is r2. And we know that due to the conservation of angular momentum, v0 r1 will be equal to v0 dash r2. So v0 dash will be equal to v0 r1 by r2. So v0 dash will be equal to v0 and multiply by r1 by r2, and the value of v0 which we have already calculated is this one. So you can see that there is a root of r2 by r1, and if we will multiply this complete expression with r1 by r2 like that, this r1 by r2, so we can say that there would be r1 by r2 inside the root. So this expression would be under root of 2gm into r1 by r2 divided by r1 plus r2. Okay, you can see that. So this is the new velocity with which this planet would reach the apogee of this elliptical orbit, this point. And this at this point we again need to fire a rocket in such a way such that it comes into the that circular orbit, new circular orbit. So for new circular orbit, we know that v2, the new orbital velocity, was under root of gm by r2, which we have already written in this case. This is under root of gm by r2, the new orbital velocity. So the rocket, now you can compare this term and this term, so it would depend on the various values of r1 and r2. So let us suppose that v2 is greater than v0 dash. We are just assuming that v2 is greater than v0 dash. So let us write down delta v, which we need to give. The second impulse which we need to give would be v2 minus v0 dash. So delta v2 should be equal to, this is under root of gm by r2 minus under root of 2gm r1 by r2 into r1 plus r2. This is r2. Okay, so let us take out the common terms, which is gm by r2, and in the bracket it would be 1 minus under root of 2r1 by r1 plus r2. You can also compare this impulse with the initial impulse. This was the initial impulse. Okay, so these are the two impulses which should be given to the satellite at perigee and at apogee, so that it starts from the orbit of smaller radius r1, circular orbit, and it goes into the bigger circular orbit of radius r2. Now we can also find out the time taken by the orbit to get transferred, by time taken by the satellite to get transferred from one orbit to another. So this let us again analyze that this is the elliptical path, and this is the planet, this is the center of the planet, this point is perigee, and this point is apogee. So we know that the time taken by the satellite to move from this point to this point is the half time which is taken by the satellite to complete the motion of complete motion of the elliptical path. So we know that this time taken would be equal to the area covered by the radius vector. This is the radius vector. So you can see that when this radius vector would revolve from this point to this point, then the area it would cover would be this one, the half area of the ellipse. So this time taken would be area covered upon the aerial velocity, dA by dt. Or we can also write down that dA by dt is equal to L by 2m, where L is the angular momentum and area covered is pi AB by 2. Okay, so this is pi AB by 2, and the time taken by this satellite is, let's suppose, T naught, and this is L by 2m, and L, we can write down the L as m into r1 into v naught, which we have already calculated that at this point the distance of planet from the center of distance of satellite from the center of the planet is r1, the mass of the satellite is m, and its speed is v naught. So the angular momentum is m r1 v naught. We have already calculated the value of v naught. So the time taken t naught would be equal to pi AB into m divided by angular momentum, which is m r1 into v naught. And we know that A is equal to r1 plus r2 by 2. And to calculate this time, we need to have the data of semi-minor axis, or we need to have the value of eccentricity of this elliptical path. So by that we can find out this. So let me tell you that how would we get that. You can see that we know that r1 is equal to a into 1 minus e. So r1, this is a is the semi-minor axis. So we know that this distance is a into 1 minus e. So r1 is equal to a into 1 minus e. Okay, so we can find out the value of e. So r1 by a is equal to 1 minus e. Okay, and e is equal to 1 minus r1 by a. And we know that e is also equal to under root of 1 minus b square by a square. So by comparing these two, we can see that 1 minus r1 by a whole square is equal to 1 minus b square by a square. So you can see that this is 1 plus r1 square by a square minus 2r1 by a is equal to 1 minus b square by a square. Cancelling this one with 1, so you can find out the value of b. So the value of b will be equal to, in fact you can see that b square by a square is equal to 2r1 by a minus r1 square by a square, and b square is equal to 2r1 a minus r1 square, and b is equal to under root of 2r1 a minus r1 square. Okay, and we know that the value of a is equal to r1 plus r2 by 2. So if we substitute this value here, so b will be equal to under root of 2 R1 into A, where A is R1 plus R2 by 2, and there is R1 square minus R1 square. Okay, so you can find out the value of B. It is under root of R1 square plus R2, this is R2 R1 minus R1 square. So cancelling this R1 square, so B is equal to under root of R2 R1. So this is the value of semi minor axis, and therefore the time period T naught, which is pi AB upon R1 V naught. So this is pi AB. In fact, there would be a 2 also, because we are finding out the half area of this ellipse, and this half area is A1. So A1 is pi AB by 2, which I have already taken in account. This is pi AB by 2 and this is T naught, so I have already taken that 2, so it is not required here. So the value of time which satellite would take from to move from this point to this point is pi AB upon R1 V naught. So this is time is equal to pi AB upon R1 V naught, and time is equal to pi, where A is R1 plus R2 by 2 and B is under root R2 R1, and here it is R1, and V naught we have already calculated initially. So this time would be taken by the satellite to move from the perigee to apogee. Thank you.